Hello everyone, I am Mitali Pal and today we are going to discuss a very important and scoring topic for the exam preparation. This is what is that? Coordination compounds. So this topic is very important because every year you are going to get lot of questions from here and it's very easy to understand. Once you understand the topic, it's very easy to score from here. Okay, so let us start. uh, okay, today we'll start with addition compounds, and then we'll go what is double salt and coordination compounds, then Werner's theory, which is the father of coordination chemistry, and obviously we'll keep the previous year questions, which are very important to see the questions so that you will understand how easy this to solve after you get the concept of coordination compounds. Okay, so let us start. So by definition, what is addition compounds? Addition compounds are made up of two or more. So it should be at least two compounds, stable compounds, by crystallization in a fixed stoichiometric ratio are known as addition compounds. Let us understand this definition with some examples. You see here example of first one, KCl, potassium chloride and magnesium chloride. So these two are two stable salts, right? So when they are dissolved in water, so they are water soluble, and then when a saturated solution is made from here. So what is saturated solution? When the maximum amount of these two salts will be dissolved and the ratio should be fixed. Okay, so 1:1 ratio means the molar ratio should be same, 1:1. Always it should be 1:1. 1 mole, if we take 1 mole of KCl, 1 mole of magnesium chloride, you have to take 2 mole KCl, 2 mole magnesium chloride. Okay, and then from the saturated solution, so what is saturated solution? Let's say take an example. If I give you 1 glass of water and 1 kg packet of stable salt, and I tell you to dissolve all the salt in 1 glass of water, so it will not dissolve all the salts, right? So at some point when you are adding 1 by 1 spoon, and at some point what will happen? It will stop dissolving more amount of salt. So that means it reached its saturation point. Okay, so why saturated solution is important? Because from there it's easy, the crystallization process starts. Okay, so after this from that solution, these two salt will crystallize together to make a solid crystal of the addition compound, and you see they will be it can be written as in dot dot, and 6H2O, 6 moles of water will be trapped inside the crystal structure of the carnallite. This is carnallite. Okay, good. And then you can see the next example where copper sulfate and ammonia is used. So 1 molar ratio of copper sulfate and 4 moles of ammonia will make another addition compound. Okay, so if you take one in excess amount, so that will remain as excess, that will not take part in forming the addition compound. So similarly, last one is a potash alum, which is a very formed from potassium sulfate and aluminum sulfate, two stable salts, right? So these are all addition compounds, and they have they were mixed in a fixed stoichiometric ratio. Okay, so that's why the addition compound formed. So why it is important? So these addition compounds are of two types. One is double salt and another is coordination compound. Now, okay, so now we'll understand what is the difference between a double salt and a coordination compound, right? So, double salt by definition, these are the compounds which will completely lose their identity in aqueous or molten state. Means the crystals of the salt, if again dissolved in water, let's say this is a potash alum again dissolved in water, so it will be dissociated to all its constituent ions. Okay, but water will not dissociate because it is a covalent compound. These are the ionic salts. Okay, they will again dissociate to all its constituent ions. So that means it is losing its identity. It is completely dissociating, right? Similarly, this is the example of more salt. So same thing is happening as these salts or these double salts will completely dissociate to its ions and lose their identity. Okay, and also in molten state it is same. So that means these are double salt. But then what about the coordination compounds or complex compounds? So these compounds actually will retain their identity in aqueous or molten state. So this is an example of a coordination complex. Okay, so when it is dissolved in water, what will be seen? That potassium ions will be observed. Okay, because if we do the test for potassium ion, let's say, so we'll get a positive test. Okay, but will not get a positive test for iron ion. Why? Because the portion which is inside the square bracket, that will remain intact like this as an anion here. In this case it is an anion, so it will remain intact. The bond between the iron and the cyanide ligand, that will not break. That is actually one kind of coordination covalent bond, so that will not break. It will retain its identity. Only the ions which is outside the square bracket, that can dissociate into ions, but the entities which is inside the square bracket, that will keep its identity intact. Okay, so that's why these will be called as coordination compounds, which are retaining their identity in aqueous or molten state. So this is the difference between a double salt and a coordination compound. Okay, now we'll go to the starting of this. Who was a Werner's? Werner was the father of the coordination chemistry. He started his research on this in 1893, and also he got the Nobel Prize for his remarkable discovery. Okay, so what he did experiment wise, so he prepared some complexes from two stable compounds. Okay, like cobalt chloride, and ammonia. Okay, so what was his observation? So when he kept the moles of the cobalt chloride same, 1 mole, and then molar ratio, but he changed the molar ratio of ammonia. 1:6, 1:5, 1:4, 1:3, 1:2. Okay, like this. So when this addition of ammonia is different in different ratio, what he observed, that different colored compound is forming. For 6 mole of ammonia and 1 mole of cobalt chloride forming a yellow colored compound, and this one with 5 ammonia, purple color, 4 green, 3 violet. Okay, then with water again it is a different colored compound. So this was very fascinating and interesting result what he got. So further, for the further study, what he did, he added excess amount of cold silver nitrate solution to it to check actually what is happening. So he got the white precipitate of silver chloride. Then he collected the precipitate and find out the mole amount of silver chloride. So what he observed, for the yellow compound, 3 moles of silver chloride formed. For purple, 2 moles, green, 1 mole, violet, 0 mole. So no precipitation here. And for this also 3 moles of silver chloride he observed. Okay, so this was the work of Werner. So then next he actually, to explain his experiments, okay, to explain that what compound actually formed, he given some postulates from his experiments. Okay, so what then actually the concept of the coordination compound, he given this concept. Okay, so he told that first complex, which is 1:6 ratio of cobalt chloride of ammonia, it may be forming this type of complex. Okay, this type of complex where this portion is inside the third square bracket and 3 chlorides will be outside. When this is dissolved in aqueous solution, so this portion will be ionized. Okay, according to this complex salt, and this portion will retain its identity. So 3 chlorides will be obtained from this complex, and then 3 chloride when silver nitrate will be added to these 3 chloride ions. So 3 silver chloride, 3 moles of silver chloride will be precipitate out from here. Okay. So he actually given totally a new concept of coordination compounds. For the second compound, you see second compound when 5 mole of ammonia is there. So 2 mole of silver chloride he obtained. That means the formula of the complex must be like this. Okay, cobalt, ammonia, whole 5 chloride and outside 2 chloride because 2 mole of silver chloride. So from these things he given the formula of the coordination complexes. So we can see first one 3 chloride outside, second one 5 ammonia, 1 chloride inside and 2 chloride outside. Okay, similarly here in case of when water is also added, water will also act as a ligand and Cl3. So ligand is what? Ligand here, ammonia is a ligand, chloride is also ligand, water is also ligand. Ligands are those species which are having lone pair of electron, which it can share with others who are having electron deficiency. Okay. So more on ligands we can discuss later. So based on his experiments, what Werner proposed, he proposed that coordination complexes have 2 types of valency. One is primary valency, in short PV, and secondary valency SV. Okay, so and he told the primary valency is ionizable. So this is one example of coordination complex. So okay, like this. So this is coordination sphere. Okay, and the ligands which is outside the coordinate sphere, those are ionizable. Okay, and those are having ionic interaction with the metal ion, central metal ion. That's why when it is dissolved in water, this portion will be ionized because they are having ionic interaction. But the ligands which are directly bonded with the metal atom, that will not dissociate because they are forming coordinate covalent bond with the metal ion. So it is hard to break, and this will not break in the only in aqueous medium. Okay, so these are making aqua ionizable, and these are non-directional because they are having ionic interaction, so they can have interaction from any side. Okay, because ionic interaction is non-directional, right? So primary valency, how you can find out the primary valency? By calculating the oxidation state of the metal ion. That way primary valency can be obtained. And secondary valency, what he told, that is non-ionizable. You see here these ammonia ligands and the chloride ligand which is inside the square bracket, okay, that is not ionizable because they are making a strong bond, covalent bond, right? Okay, and they are directional in nature. You see they are formed in a particular direction. Okay, so now what is so these bonds will decide the coordination number of the metal ion. So secondary valency is actually the coordination number of the metal ion. Now what is coordinate covalent bond? Do you remember? Okay, let's revise it. So coordinate or additive bond, it is one kind of covalent bond only, but the shared pair of electrons will be donated or will be given by one atom. You know, covalent bond is sharing of electron, one electron by 2 atoms. Okay, and they share and they make a covalent bond. Their orbitals overlap. But in case of dative bond, it's covalent bond only, sharing only, but only one is electron rich, another will be electron deficient. So one will give, another will take. Okay, you see this is example of ammonia and H plus. So H plus have no electron. Normally hydrogen has 1 electron, but H plus, because it's plus, there will be no electrons. Like this, one shell will be there, no electron. Ammonia, so this ammonia, how ammonia molecule forms, and nitrogen is having 5 valence electrons. X, with X it is denoted. So 3 is unpaired and 2 is paired electron. Now these 3 unpaired electron will be shared by 3 hydrogen atoms. It will be, this is a covalent bond, normal covalent bond it will make, okay, because it is equal sharing. One electron is coming from the one hydrogen, another electron is coming from the nitrogen. They are both unpaired and now they will pair up. They will share their orbitals, share their electrons, overlap the orbitals, and then it will form. But what about the lone pair of electron? So this lone pair of electron, it is having who is electron deficient, it can actually share with electron deficient species like H plus. So you see here, so this given in blue color, so this is actually nitrogen is sharing with the hydrogen, so hydrogen is also using it to complete this doublet to get stabilization, and nitrogen is also sharing it to make it octet complete. Here also it was complete, it was octet was complete. So ammonia is a stable molecule only, okay, but it is itself also stable, but it can also donate its electrons, share its electrons, and can make other species also stable, okay. So this way cooperative bond or covalent coordinate bond forms, and this type of bonding will form in the metal ligand complex, okay. And the another postulate of Werner is the geometry of the complex is decided by secondary valency. Why? Because the secondary valency as directional, they are having particular, because the orbital overlap will happen. Okay, so you see these bonds will form. No, these are the examples of uh, these are the examples of different geometry compounds. You see, these are the bonds which are forming. So that is in particular direction. Because 6 bonds, this is octahedral complex. 6 bonds are forming around the cobalt atom or ion. So they are in the different direction. Okay, and it is making the octahedral shape. For if the ligand number is 4, there are two types of geometry possible: square, planar, or tetrahedral. Okay, so that means the ligands which is directly bonded with the metal atom, so that is deciding the geometry because they are directional in nature. Okay, so secondary valency decides the geometry of the complex, right? I hope you understood till here, until here. Okay, now we can discuss some previous year question only on the concept of the Werner's experiments. Okay, you see that so many question is coming only on the concepts of Werner's experiment. Okay, the ionizable, which ligands are ionizable, which ligands are non-ionizable. Okay, so on that particular concept, question is coming every year in alternate year, and rest of the portions so I leave. There are a lot of other things is there: primary valency, secondary valency, then ligand system, then isomerism. So many other things are there. Now we are going to discuss just from the Werner's concept what are the previous year question came. Okay, so same concept, how the same concept is used repeatedly, and the way of the question is just changed. Okay, the way of the question is changed, but the concept is exactly same. Okay, so it's so easy. You see, in NEET 2017, what came? The correct order of the stoichiometries of AgCl formed when silver nitrate in excess is treated with the complexes cobalt chloride 6 ammonia, cobalt chloride 5 ammonia, cobalt chloride 4 ammonia respectively. So it is asking directly from the Werner's experiment how many moles of silver chloride will form. So we have just seen it in the table of the Werner's experiment. This was a table. So when cobalt chloride 6 ammonia is there, the yellow compound forms. We see the complex formula must be like this, where 6 ammonia is directly bonded and 3 chlorides will be outside the bond. So this will 3 chloride will be precipitated as silver chloride. In this case, when 5 ammonia, so 2 chloride, because it is making octahedral complex, so 5 ammonia and 1 chloride will make, because octahedral, so there should be 6 ligands attached to the metal atom, so they will be making 2 moles of silver chloride, and then 4 ammonia will give 1 mole of. So you see the question. So we let us see the another question. This come in 2001. So what it is asking, that which of the following will exhibit maximum ionic conductivity? So here some example of coordination complexes is there. So ionic conductivity, it depends on number of ions. So if more number of ions are present, the ionic conductivity will be more. Okay, so among these complexes, how many numbers of ions will produce? Let's see in the next slide. Okay, so the first one, we can see that total ions, you see in aqueous solution, it will give 4 potassium ions, and this will remain intact. So this is 4 plus 1, so 5 total ions. This one is how many? 3 plus 1, 4 total ion. So this one will, this portion will be remain intact, and 2 chlorides will be there, total ions will be 3. Then nickel, this compound, so this is a neutral compound itself, so it will not dissociate, total ions will be 0. So it is asking that exhibit maximum ionic conductivity. Okay, so obviously total number of ion, in the first case it is maximum, so the ionic conductivity will be maximum for this complex. So the concept is same. You see, for the first question, how many AgCl will form, and now this one also, which will show maximum conductivity, means you have to know how many ionizable ions are there. Okay. Here again you can see in another NEET question that excess silver nitrate is added to 100 ml of 0.01 molar solution of tetra chromium chloride. The number of moles of AgCl precipitated would be. Okay, so this question is also from the same concept, how much mole of silver chloride, but the mole concept is also integrated in this question. Okay, so we can see from this this concept of this Warner's experiment, the question can be formulated in so different ways. Okay. Okay, the same question is coming in alternative year, we just in different way. Okay, so it's very scoring and important chapter for all of you, so you try to solve it by yourself. Okay, so today I'll finish my lecture here. Thank you for listening.